Okay, this is session 1, ratios, scientific notation, per capita, and proportions. My name is Ryan Pennell. This is August 18th, 2021. What is due tonight? Nothing. There's nothing due tonight because tonight is the first night of class. What is due next Tuesday? Our assignments are going to be due Tuesdays at midnight, 11:59 p.m. Eastern Standard Time. We will have a rounding review, discussion 1, homework section 2, that's section 2 from the book, homework section 3, and a quiz. Okay, so all of those are listed under module 1. Right, you'll need to take a look at that. Next thing we're going to do is we're actually going to take a look at the content involved within those homeworks and quizzes. First thing I want to look at is ratio. A ratio is a comparison between two numbers. An example might be 3 to 2. Okay, this would be a ratio. We can write this in various different ways, such as 3 to 2, 3 per 2, and then 3:2, which is also said as 3 to 2. 3 divided by 2, or 3 over 2, would be that fraction there, and that is another way of writing it. And then 1.5 is the decimal representation of that ratio, and we can write that all different ways. Those are all the same thing. Another example might be 12 to 15. This would be 4 to 5, 4 per 5, 4 to 5 with the colon there. 4 over 5 is a fraction, or 0.8, which would be the decimal representation. 7 to 3, okay. Well, 7 to 3, 7 per 3, 7 to 3 with the colon there, 7 over 3, or 2.3 repeating. This has a repeating decimal there, and that would be the way of representing it with a decimal. Okay, those are all equivalent. Okay. When we will be asked to write a ratio as a sentence, this is useful when the units of two objects are not the same. This is a comparison between two quantities. So an example of a ratio, 12 apples to 8 oranges, could be written as 12 apples over 8 oranges, or 3 over 2 oranges. There I reduce those numbers. Since they both have 4 in them, I can take the 4 out. 3 times 4 is 12. 2 times 4 is 8, so I can take the 4's out, and then this is an equivalent ratio, 3 divided by 2, or 1.5 as we saw before. So 3 apples to 2 oranges. A sentence would be, there are 3 apples for every 2 oranges. When we write our sentences, it is usually best to write them as a reduced number like this. Let's look at another example. Write a sentence comparing 21 students to 3 teachers. Okay, so this is another example of a similar thing. If we can, we'd like to reduce these numbers if that's possible. Okay, and 21 and 3 are related. So 21 divided by 3 is 7. So I could just write it as 7 students to 3 teachers, or to 1 teacher, excuse me. So there are 7 students for every 1 teacher. Okay. Next thing, when using ratios, we may need to convert the units to match numbers. So often they don't have the same units. Let's look at an example that will explain that better. So a ratio of 9 inches to 3 feet. Well, inches and feet are very related, but they're different also, right? So there's inches in a foot, right? There's 12 inches in a foot, and it would be much more convenient if I use this as the same unit rather than having two different units there. So let's do that. If I convert the 3 feet into inches, I could go 3 times 12, which gives me 36. So there's 36 inches there. Next, I'll go 9 inches over 36. That gives me 1/4, okay, a quarter. All right, so then there's 1 to 4 feet. This is better when describing a ratio that we have it as reduced as possible and also in the same unit, so it's easily understood what is meant by this ratio. Another example, a firehouse cooked 780 pieces of chicken for an estimated 240 people. Well, these aren't units that we need to convert, right? I mean, chicken and people, those are two different things, just like apples and oranges. But we could reduce those numbers significantly. So we have 780 over 240, that's 3.25 or 3 and a quarter. So as a sentence, I could write, for every person, the firehouse cooked 3 and a quarter pieces of chicken. Okay, so everyone could have that much chicken, and that would be the most that they could have, or everyone could have 3 pieces of chicken. All right. All right. Next thing is part to part or part to whole. Well, this is a definition in our book, and it's about comparing ratios. Okay, so when we're comparing these ratios, sometimes we're looking at part to part or part to whole. Part to part has to do with comparing two parts of a system. Okay, so part to part describes two quantities that are subsets of the larger group. In other words, both items are not the total of the group, but smaller portions. So I could say, well, in this class, there is 2 boys for every 3 girls. Okay, well, that's not comparing to the entire class. That's just comparing, particular people in the class. So it's not the entire class. Part to whole is that where you compare to the entire class. So part to whole is the comparison of total group, entire group. The ratio is unique and then it can be written as a decimal when it is written, converted into a percentage. Okay, so we can convert that into a percentage. You can make a decimal become a percentage by moving the decimal point to 2 places. All right, so if you want to convert something in a decimal to a percentage, you just move the decimal around. Okay, so if you have 0.8, you could just move the decimal 2 places to make 80%. We'll see some examples of that. Let's look at an example now. In a class of 20 students, there's 12 women. Find a ratio of females to the total class written as a reduced fraction. Then write the sentence to describe this ratio. Okay, so we have 12 women, but 20 entire students. Okay, so 12 women over 20 students is 3/5. Okay, so there are 3 women in the class for every 5 students. Okay, there. Not so bad. This would be a part to whole example. 60% of the students in the class are women. So if you look at 3 divided by 5, that's 0.6. We can move the decimal place 2 spots. That gives us 60%. So 60% of the students in this class are women. Okay. Next type of ratio I want to look at is age dependency. Okay. One application of a ratio for our country is to apply them to an age dependency. 3 categories: children, working age, and elderly. Well, we know in real life that this isn't always quite right, but this is how it is defined in statistics. So the working age from 15 to 64 could be considered a little outdated. We know that the working age is actually going up, so people are working later in life, and that's true on the tail end as well. People are working past 64, 65, into their 70s. So we keep this, but this is an average, okay? And elderly is considered 65, but we know that 65 is actually a little bit on the younger side in recent times. Okay, for this class, we'll have 3 ratios that can be found, the groups based on the working class. So a child dependency ratio, children divided by the working. Old age dependency ratio, elderly divided by the working. And age dependency ratio, children plus the elderly divided by the working. Okay, so if you want child dependency ratio, you would take the number of children divided by the number of people in the working age. If you want the old age dependency ratio, you take the elderly people, the people that fit in the category of 65 and older, and divide them by the working age. And if you want age dependency ratio, this would be children plus the elderly divided by the working age. Notice that all of these are a part-to-part ratio. None of these are part-to-whole because all of them are compared to the working age and not to the entire population. So here, using the information below, calculate the dependency ratio, round the decimal to the thousandths place. Okay. Let's look at the child dependency ratio. So in this example, there's 625 children, and for the working age, there's 1,800. So I can divide that, I can reduce that fraction to 25 over 72, and this would be the child dependency ratio. Let's look at the old age dependency ratio, elderly divided by working. In this example, there's 455, so that'd be 455 divided by 1,800, okay? And if we reduce that fraction, that would be 91 over 360. All right. Age dependency ratio. Now remember, this is children and the elderly. We have to add them together. So in this example, that's 625 plus 455 divided by 1,800, and that is 3/5. Okay, so this is an example of all three of those ratios. They're very important. We'll be expected to do them in our homework, on our quiz, on our exams, and I hope that that is a good enough example to get you started. Okay, let's also look at scientific notation. All right, now scientific notation can seem really complicated at first, but surprisingly, it's actually just a way of writing down numbers. It doesn't really have a deeper meaning to it. It's just a notation, way of writing something down, to simplify very large and very small numbers. Here I've written some examples of scientific notation. This is what it looks like. So 1.23 times 10 to the 2, or squared, sometimes we say squared. 5.1 times 10 to the 9th. 3.007 times 10 to the negative 6. And 6.6802 times 10 to the negative 100. These are all examples of scientific notation, but I want to show you where do these numbers come from. Let's look at a table, and I think it will become more clear. So if we look at this table, we have 1 through a billion. I'm going to skip a couple numbers, but I think this will become clear of how scientific notation is built. So 1 can be written as 1 times 10 to the 0th. Notice with 1, there's no zeros at all. So I can write 0 there. And that's also true because anything to the 0th is 1. So this is really just 1 times 1 equals 1. Okay. But 1 times 10 to the first is also 10. Okay, 1 times 10 is just 10. But notice with the exponent that there's just 1 0. Okay, so with the number 10, there's 1 0. And with 1 times 10 to the first, that first up there is referring to that 0. So if logic prevails, then the 100 is going to have 2 zeros. There it is. So 1 times 10 squared. Okay, so there's 2 there. So 1,000 will have 3, 10,000 has 4, 100,000 has 5, a million has 6, and the next number is a billion and it has 9. Okay, trillion would have 12. So this is hopefully fairly simple. We're just counting the zeros. That's the only thing that exponent does for us, is just count the zeros. Nothing more, nothing less. All right, well, what about those negative exponents that we saw earlier? So I made this chart. And we'll start with 1 again, which has no zeros at all. And next we'll look at a tenth. 1 divided by 10, or 0.1. That has 1 0, but it's less than 1. So that has a negative 1 exponent. The negative tells us that it's less than 1. So this is a 0.1. It's 1 order of magnitude less than 1. Okay, again with 1/100th, that is negative 2. Okay, there's 2 zeros there. Notice that we always count the 0 to the left. There's 2 zeros there. Okay, so 1/1000th is 3. 1/10,000th is 4. 1/100,000th is 5. 1/1,000,000th is 6. And 1/1,000,000,000th is 9. So if it's less than 1, we have negative exponents, okay? But it still corresponds with the number of zeros, just like it does with numbers greater than 1, okay? So I hope that kind of makes it evident of where these numbers are coming from. Okay, let's look at some examples together. So I'm going to turn some normal numbers into scientific notation. The first one I'm going to do is 32,000. So see here, we have 3.2 times 10 to the fourth. Well, you may say, hey, there's 3 zeros there. Why didn't you make it 32 times 10 to the third? And the reason for that is because we're only going to have one number to the left of the decimal place. So we need 3.2 times 10 to the fourth, okay? Not 32 times 10 to the third. This is a standard procedure of scientific notation. The next one I want to do is 320,000. This is going to be 3.2 times 10 to the fifth. Again, we only have one number left of the decimal place. So we have 3.2 again, but that will be 5 places we move the decimal place. So I need times 10 to the fifth. The next one I want to do is this 0.0022. Okay, what would that be? Well, that's 2.2 times 10 to the negative third. I would need to move that decimal place 3 times to get it in between those twos. So that's a negative exponent since I'm moving it to the right. For the next one, it's 4.04. I can't lose that 4 at the end, so I have to include it. So it's 4.04 and not just 4.0. And that's times 10 to the negative fourth. That way I don't lose any information. Okay? Hopefully that helps. Let's look at some more examples. Next example I'm going to do is 12,000. This is going to be 1.2 times 10 to the fourth. Again, we only have one number left of the decimal place, and I have to move it to the left 4 times. All right. Next example is kind of confusing. It's 62.1 billion. Okay. Well, a billion has 9 zeros. We saw that before. With 9 zeros, you would think it would be 62.1 times 10 to the ninth, but actually it's going to be times 10 to the 10th because we need to only have one number to the left of the decimal place. All right. This next one, hopefully it makes sense. We just need to get the decimal place between the 8 and the 4. We see that that has happened here, 8.41. I had to move the decimal place 5 times to get it between that 8 and the 4. And since that is a number less than 1, it has to have a negative exponent. The very same for the next example. I just want to clarify that we can't lose any information, so that has to be 9.009. We need to tack on that last 9 so we don't lose any information. And I had to move the decimal place 7 times to get it to that spot, so that would be to the negative 7th. All right, well, hopefully that helps. Let's now talk about how we could multiply and divide numbers that are in scientific notation. When dealing with scientific notation, you can multiply or divide numbers by keeping the times 10 to the n in your answer. The times 10 to the n, that n there, I'm just saying that could be any number, okay? Now, when multiplying numbers in scientific notation, exponents will add. When dividing them, exponents will be subtracted from the top number, bottom number. So those are going to be subtracted. Then do the operation required, multiply or divide. Note the correct way to write a scientific notation. Okay, so let's take a look at an example. I think it's going to clear it up a lot. Multiply the numbers 1.1 times 10 to the second with 6.7 times 10 to the fourth. Okay, first step is to multiply the numbers in front. 1.1 times 6.7, that's 7.37. Next step is to deal with those exponents. So since we're multiplying, we're going to add the exponents. So 10 squared times 10 to the fourth, that's 2 plus 4, that's going to give us the 6. So grand total, 7.37 times 10 to the sixth. Okay? All right. Fair enough, but let's look at another example. Multiply 5.5 times 10 to the third with 6.0 times 10 to the fourth. Okay, I'm going to multiply those numbers up front. That's going to give me 33. Then times 10 to the third times 10 to the fourth. You can add the exponents. 3 plus 4 is 7. Oh, but that's not times 10 to the seventh. Remember, since that was 33, I can only have one number to the left, so I'll have 3.3 times 10 to the eighth instead. All right, let's look at some division examples. Divide 6.92 times 10 to the 16th by 5.0 times 10 to the 13th. First step, again, let's divide the numbers in the front. So 6.92 divided by 5 is 1.384. Okay, nothing new there. But what do we do with the exponents? Since we're dividing, we subtract the exponents. So 16 minus 13 is 3, of course. So I'm going to round this to 1.4 times 10 to the third. Since that's the most specific I can give it, I have to round it a little bit. Let's look at another division example. 1.99 times 10 to the 6th divided by 4.20 times 10 to the first. First step I'm going to do is divide those numbers up front. So 1.99 divided by 4.20 is 0.4738. We notice that that number is less than 1, so I know in the end I'm going to have to move that decimal place a little bit. All right, next up, let's look at the exponents. So since we're dividing, we'll need to subtract. 6 minus 1 is 5, of course. All right, well, the final answer has to be 4.74 and not 0.47. So I had to move the decimal place. Since I made the number larger, I have to make the exponent smaller. So I moved the decimal place 1 to the right, so I have to change the exponent down 1. All right, hope that helps. Next idea I want to look at is per capita. So a useful ratio that compares people is called per capita. Per capita, I believe, has to do with the phrase in Latin, Roman times, per capita. So it has to do with like per person. Per capita means like people in the population. Okay. So this stands for per person and is a fraction of items divided by people. A sentence has the form objects per person, meaning several items for one person. So calculate the money per capita if there is 1,800 million for every 0.79 million people. So we want to do per capita. Let's do it. So that's 1,800 million divided by 0.79 million. Well, since it's million over million, those are going to cancel, so I can get rid of that. And then what do we have here? 1,800 divided by 0.79. This is going to be $2,278.48 per person. Okay, per capita means per person. You can just exchange that. Let's look at some more examples. All right, let's look at this. So this is an example of a homework problem. And we have companies alpha, beta, and gamma. We have number of projects, number of employees. We want to find projects per capita, projects in scientific notation, and projects per 100,000. We'll talk about per 100,000 in just a moment. We're given a head start with the per capita. Notice that it's the number of projects per 35.2 million people, so we got to watch those zeros. All right, so the next thing is I'm dividing that 7,144 by 325.7 billion. So I get a very, very small answer, and that's going to happen with the next example. Notice the million written there, so that's going to really affect those zeros, of course. We can rewrite these numbers in scientific notation, just as we see here. Now, with the per 100,000, you need to multiply by 100,000 people. So these will change the numbers in this way. And per 100,000 people, remember, it's not per person anymore, it's per 100,000. So you need to multiply that by 100,000 to find that, okay? Proportions. Let's talk about proportions. Now, proportions can be a little bit tricky if you haven't been in algebra class in a little bit. So let's talk about how we do it. So let's say 16 divided by 29.2 is equivalent to an unknown number divided by 42. How can we solve for this? We can cross multiply. So 16 times 42, 29.2 times x, we get this equation. We can divide both sides by 29.6 to find our final answer. Okay, so this is how you can do proportions. You're just doing cross multiplication. It should only take you a couple steps. Okay, let's look at more examples to get more comfortable with this. Another proportion, 181 divided by 67.5 equals 672 divided by x. X is the unknown number. We want to solve for that. We're going to use cross multiplication to solve for such a thing. So that's what I'll do here. And then I find 181 times x equals 672 times 67.5. We divide both sides by 81. We find 250.6. All right, fairly straightforward. Let's look at a word example, how this might apply to real life. A pack of 40 paper clips cost $9.20. If you spent $28.50 on paper clips, how many did you buy? I'm going to set up the proportion now. So for every 40, it costs 920. We have an unknown amount of paper clips at $28.20. We can solve using our cross multiplication. I've done that here. 40 times $28.20 divided by 920 is 124 paper clips, rounded, of course. I had to round up a little bit. But that is how many paper clips. So things are proportional. It's a fundamental thing of mathematics that we're able to do these proportions, and I hope that gives you a head start of how to do them. All right. What's due tonight? Nothing. There's nothing due tonight. Great news. The bad news is there's a lot due Tuesday. Rounding review, discussion 1, homework section 2, homework section 3, and a quiz over all 3 sections. Okay, the quiz has a little bit of the syllabus in there, and then some homework 2, homework 3 section in there. Okay, well, I hope this gives you a head start. I hope this provides you with a little knowledge of getting going, getting started in this class, and I hope you find it as enjoyable as I do. And I will see you next time.